Lecture 23, Radioactive Decay, Kinetics and the Band of Stability. In a previous lecture, you were introduced to radioactive decay and the different forms it can take. We looked at alpha, beta, and gamma emission, positron emission, and electron capture. The next step is to look at how we can predict which nuclei will be stable and which will be unstable. To do this, we're going to draw an analogy to the atom. We learned in Chem 1 that atoms that have 8 electrons in their outermost shell, or an octet, tend to be most stable. Those elements that do have 8 valence electrons are the noble gases, which we know to be relatively stable and very unreactive. The nucleus of an atom behaves in a very similar way. First thing you should know is that protons and neutrons are held together in the nucleus by what's known as the strong nuclear force. Like electromagnetism, which holds electrons to the nucleus of an atom, the strong nuclear force is a fundamental force that only takes effect when protons and neutrons are very close together. The strong nuclear force has to fight against the electromagnetic force, which wants to separate protons which have a like charge and repel one another. Now, protons and neutrons also, like the electron, have a half-integer spin. We learned in Chem 1 that there's a spin quantum number that electrons have that can take a value of plus or minus 1/2. Protons and neutrons also have a spin quantum number of plus or minus 1/2. Also, protons and neutrons are arranged in energy shells within the nucleus that follow the same rules that electrons follow when occupying electronic energy levels. They follow the alpha principle, which states that lower energy shells are filled before higher energy shells, and a Pauli exclusion principle, which says that no two nucleons have the same 4 quantum numbers. It should be no surprise then that just like how having an octet of electrons is a very stable configuration for atoms, having a certain number of protons and neutrons also make a stable nucleus. We call the number of protons and neutrons that a stable atom can have the magic numbers. Please keep in mind that you do not need to memorize the magic numbers. We're just using them to draw an analogy as to what makes a nucleus stable. The magic numbers are 2, 8, 20, 28, 50, 82, 126, and 184. A good example of a stable nucleus that has a magic number of nucleons is the helium-4 nucleus, which has 2 protons and 2 neutrons. We know that the helium-4 nucleus is also an alpha particle. The reason why the helium-4 nucleus is lost during alpha decay is because it's a very stable piece that a nucleus could actually lose. Another predictor as to whether or not a nucleus will be stable is to look at whether or not the number of protons and or neutrons are even or odd. It turns out if there's an even number of protons and an even number of neutrons, that the nucleus is more likely to be stable. As you can see in the table to the right, an even number of protons and even number of neutrons have more stable isotopes than having an odd number of protons and an odd number of neutrons. It's really interesting to note that one of perhaps the most famous examples of a stable nucleus that has an odd number of protons and neutrons is the nitrogen-14 isotope, which is the most stable isotope of nitrogen. This isotope has 7 protons and 7 neutrons. It is one of the 5 stable number of isotopes that exist. Another helpful predictor of what the types of stable nuclei and looking at the types of radioactive decay a nucleus will undergo to become stable is making a stability plot. The stability plot to the right shows a plot of the number of neutrons versus the number of protons a nucleus has. Each dot plotted is a nucleus. The stable nuclei are those black dots. We call the band of black dots there the band of stability. These are all of the stable nuclei. Unstable nuclei, which are shown by the purple dots, will try to move towards the band of stability in order to become stable nucleus when it undergoes radioactive decay. Also plotted is the number, also shown on the graph, is a red line that represents the case where the number of neutrons and the number of protons, N and Z respectively, are equal to one another. You can see that at low atomic numbers and low number of neutrons, that red line lines up almost perfectly with the band of stability. That is, that smaller stable nuclei tend to have an equal number of neutrons and protons. We see this with helium-4, nitrogen-7, and carbon-12, each having an equal number of protons and neutrons. When the atomic number gets larger, the band of stability deviates more towards having more neutrons. This is because as the number of protons increases, the amount of repulsive force is higher and more neutrons are needed to mitigate those forces. Now let's look at how we can use the band of stability to predict what type of radioactive decay a nucleus will undergo to become stable. We can use the ratio between the number of neutrons and the number of protons as a predictor. If the ratio between the number of neutrons and number of protons is significantly higher than 1, we can predict that in order to reach stability, that nucleus will undergo beta decay. This is because beta decay converts a neutron into a proton. Therefore, it lowers the ratio between the number of neutrons and the number of protons, the N to Z ratio. Nuclei with a higher number of neutrons will therefore undergo beta decay to get closer to the band of stability. On the other hand, if the N to Z ratio is significantly lower than 1, the nucleus will undergo either a positron emission or electron capture. This is because both processes convert a proton into a neutron, which will increase the N to Z ratio and move the nucleus closer to the band of stability. Please note that electron capture is relatively rare. You'll never be asked to predict whether or not a nucleus will undergo electron capture because that would be a difficult thing to predict. Therefore, we will only predict positron emission for nuclei that have a small N to Z ratio. Another interesting thing to note is the band of stability ends about where Z is equal to 83. Therefore, there are no stable nuclei that have an atomic number greater than 83, which is bismuth on the periodic table. These larger nuclei need to lose large chunks of their nucleus to reach the band of stability. Therefore, these nuclei are most likely to undergo alpha decay, which allow for those nuclei to lose those big chunks of the nucleus to reach stability. One thing you might see in your textbook is a process of a series of alpha and beta decays that a large nucleus can undergo to reach the band of stability. We're not going to worry about those types of predictions, but you should be able to predict whether or not a nucleus will undergo alpha, beta, or positron decay. Here's a summary table of the different types of radioactive decay and why they happen. Alpha decay occurs for nuclei that have an atomic number greater than 83. When alpha decay occurs, the atomic number of the nucleus that undergoes that type of decay will decrease by 2, and the mass number will decrease by 4. Uranium-238 is an example of a nucleus that undergoes alpha decay. Beta decay occurs when the N to Z ratio is large, or the nucleus has too many neutrons. In beta decay, a high energy electron is emitted, and the atomic number is increased by 1. Carbon-14, which is used in radioactive dating, undergoes beta decay. We also talked about gamma emission, which occurs when a nucleus is in an excited state. When a nucleus undergoes gamma emission, it gives off a high energy gamma photon. You do not need to worry about predicting whether or not gamma emission occurs. Positron emission occurs when the N to Z ratio is small. When positron emission occurs, a positron and neutrino is given off, and the atomic number goes down by 1. Technetium-95 is an example of a nucleus that undergoes positron emission. Electron capture also takes place when the N to Z ratio is small. When electron capture occurs, X-rays are given off, as well as neutrinos. The atomic number goes down by 1. Note that you do not need to be able to predict whether or not electron capture occurs, but you do need to be familiar with the nuclear equation for electron capture. An example of a nucleus that undergoes electron capture is the potassium-40 nucleus. Let's do an example of predicting the type of radioactive decay that a nucleus will undergo. We're going to predict the mode of radioactive decay that phosphorus-27 will undergo. First of all, we need to be able to predict what the stable isotope is. Remember what the most stable isotope is. If you look back at the band of stability, we usually want to use N to Z is equal to 1. However, remember that most of the nuclei have larger numbers of neutrons. Therefore, as a mode of comparison, we'll use the periodic table to help us determine what the most stable isotope of the element will likely be. We look at the atomic mass, which is a weighted average of all of the masses of all the isotopes for an element. We call it a weighted average because the most stable isotope or most abundant isotope tends to contribute the most to the atomic mass. Therefore, for most elements in the periodic table, we can use the atomic mass to predict what the most stable isotope is. If we look at phosphorus on the periodic table, we see that the atomic mass is pretty close to 31. Therefore, we can conclude that phosphorus 31 is the most stable isotope of phosphorus. Phosphorus 31 has 16 neutrons, which can be found by subtracting the atomic number from the mass number. We also know that phosphorus is also atomic number 15. Therefore, we can calculate the ratio between the number of neutrons and number of protons to be 16 over 15, or 1.07. Note that this is pretty close to 1, since phosphorus is still a pretty small atom. Now let's look at the N to Z ratio for phosphorus 27, our isotope of interest. The N to Z ratio for phosphorus 27 is 12 over 15, which equals 0.80. Since 0.80 is smaller than 1.07, we predict that phosphorus 27 has too few neutrons or too many protons. Therefore, phosphorus 27 is likely going to undergo positron emission, which will increase the number of neutrons. When phosphorus 27 undergoes positron emission, the number of protons in the nucleus will decrease by 1. This means that if you take away a proton, you end up with 14 protons, which gives you silicon 27. The other particle emitted will be a positron. I'll leave it up to you to write the nuclear equation for that process. The next part of our lecture takes a look at how to quantify radioactivity. We'll look at 2 ways to do this. First is just looking at how radioactive a substance is. We measure that by measuring the activity of the substance. The activity of a substance is defined as the number of radioactive decay events, or number of radioactive nuclei, that undergo a nuclear decay event per unit time. The SI unit for radioactive decay is the becquerel, named after Henry Becquerel, who discovered radioactive decay. 1 becquerel is 1 disintegration or radioactive decay event per second. Therefore, the units of 1 becquerel is equal to 1 over seconds, or seconds to the minus 1. Since the activity in becquerels looks at individual radioactive decay events, or individual nuclei that undergo radioactivity, the activity in becquerels can be a rather large number. Therefore, we can use another unit which helps to group the number of becquerels to give us a more reasonable number that's easier to compare. We do this using the Curie, named after Madame Curie and her family, who made significant contributions to the study of radioactive decay. 1 Curie is equal to 3.700 times 10 to the 10th becquerels. This conversion is an exact conversion. I've mentioned several times when we took a look at kinetics that radioactive decay is a first-order process. Let's look at how that is. When we measure the activity of a radioactive sample, we're also measuring directly the rate of radioactive decay, since we're looking at decay events per unit second. Therefore, the rate of radioactive decay, which is equal to the change in the number of radioactive nuclei present over the change in time, is equal to a rate constant, K, times the number of nuclei present at time t. Therefore, we see that the activity, or rate, is proportional directly to the number of nuclei present at any given time in a sample. This is useful to realize because this means that we can use any of our first-order integrated rate laws to do calculations that involve radioactive samples. This is very useful in doing things like radioactive dating, and the use of radioactive decay in medicine. A common instrument used to measure the activity of a sample is a Geiger counter. A Geiger counter, like the portable one shown in the picture, works by having a tube that is filled with some inert gas, such as argon. There is a window in the front of the tube that allows radioactive particles to enter the tube. These radioactive particles ionize the gas sample inside, and the ionized gas sample are detected by hitting a phosphorescent screen in the back of the tube. This phosphorescent screen converts those collisions into electricity that is routed to the detector connected to the tube. Each time an ionized gas particle is detected, an audible click is typically heard from the detector, which you might have seen in many cases of observing the use of a Geiger counter. Therefore, the more clicks that the Geiger counter makes, the more radioactive the sample is. Let's do a calculation that involves calculating the activity of a sample. We're looking at a sample of gold 198, which has a half-life of 2.69 days. We're going to calculate the activity of a sample, of a 0.86 milligram sample in curies. To start, we're going to use our rate equation from the previous slide, remembering that the rate is directly equal to the activity of the sample in becquerels. This is equal to the rate constant times the number of nuclei present at time t. To get the activity in becquerels, which can be converted into curies, we need to know the rate constant for the decay of gold 198 and the number of nuclei present in the sample. Noting that radioactive decay is a first-order process, we can use the half-life equation for first-order reaction to calculate the rate constant. This half-life equation is that the half-life is equal to the natural log of 2 over k. This means that the rate constant k is equal to the natural log of 2 over the half-life. Therefore, we can take the natural log of 2 and divide it by 2.69 days to get a rate constant in inverse days. However, we note that a becquerel is an inverse second. We should convert our inverse days into inverse seconds so that the units match up. Therefore, we convert days into hours and then into seconds, which gives us a k equal to 2.98 times 10 to the minus 6 inverse seconds. Now that we have our rate constant, we can turn to calculating the number of nuclei, which can be done with a simple mole calculation. The first thing we need to do is convert milligrams of gold 198 into grams of 198, which we can do by dividing by 1,000. The next step is to convert grams of gold 198 into moles of gold 198. One thing to note when doing these sorts of mole calculations with radioactive isotopes, the molar mass of our radioactive isotope will just equal the mass number. Therefore, 1 mole of gold 198 is equivalent to 198 grams of the sample. Now that we've converted to moles of gold 198, we want to convert to the number of nuclei, which can be done by multiplying by Avogadro's number, which is 6.02 times 10 to the 23rd per mole of gold 198. This gives us 2.6 times 10 to the 18th gold 198 nuclei. Our next step is to calculate our activity, now that we have the rate constant and the number of nuclei. We can multiply those two values together to get an activity of 7.7 times 10 to the 12th becquerels, or 1 over seconds. Our last step is to convert the number of becquerels into curies by dividing by 3.700 times 10 to the 10th becquerels. Please note that there's a typo in that conversion factor. Instead of 3,700 times 10 to the 10th, it should read 3.700 times 10 to the 10th becquerels. This gives us a final activity of 210 curies. Note that most of this problem involves lots of unit analysis and calculations that we've seen before, but used in a new context. Also remember that in all cases of quizzes and exams, you'll get equations and conversions. Now we look at how to measure the dosage of radiation received by being exposed to radioactive samples. When we look at this, there's two things to consider. Remember that radiation does damage in two ways. By imparting energy to biological tissues, which can be used to denature proteins and break the bonds that hold together biological molecules. The other type of damage that can be done is through ionization, where charged particles interact with biological molecules, which can also lead to the breakage of bonds and the denaturization of different types of tissues. Therefore, when we're measuring the radiation dosage, we need to consider energy imparted to a mass of tissue and the type of damage that it can do through ionization. Let's first look at how we measure the amount of energy imparted to biological tissues. There are two ways we can measure this, both related to one another. The RAD, which was formulated first, which stands for the radiation absorbed dose. This is the amount of energy in joules departed on a given mass of tissue. It is a way to measure the exposure to radiation. 1 rad is equal to 0.01 joules per 1 kilogram. Therefore, it's a pretty small unit. Another unit related to the rad is the gray, which is considered the SI unit for measuring radiation dosage. It is equal to 1 joule per 1 kilogram of tissue, or 100 rads. In the picture on the right, a worker is wearing a badge that measures radiation dosage in grays. Many people who work in labs where radioactive samples are used wear such badges to monitor the amount of radiation that they are exposed to. The rad and the gray are more focused on the amount of energy imparted to a biological tissue. However, if you want to also take into effect the amount of damage that radiation can do through ionization, you need to look at some other units. The REM is one such unit, which is short for Roentgen equivalent man. The REMs measure the radiation exposure, but also takes into account the types of damage that can be done to biological tissue. These types of damage depends on two things: the type of tissue, biological tissue that's exposed, such as skin, muscle, heart tissue, or mucous membranes, and also the type of damage that the radiation can do. Remember that alpha radiation, having a positive 2 charge, can do more damage than beta or positron emission, which have a smaller magnitude of charge. All of this is taken into account in the REM. These different effects can be accounted for by using what's called the relative biological effectiveness factor, or the RBE. If you take the RBE and multiply it by the dosage in rads, you get the dosage in REMs. So the REM takes into account all of the factors that measure how damaging a dose of radiation can be. This table here shows the types of radiation dosages that you can get from different sources that are common. Cosmic radiation, which are radioactive particles that come from outer space, gives you a dosage of 27 millirams per year. An airplane flight gives you a half of a millirem per hour, which is a small amount more since you are closer to the end of the Earth's atmosphere. Chest x-rays, or x-rays from at the dentist, give you between 8 and 30 millirems. A smaller amount of radiation. And radon gas, which can accumulate in the basements of many homes, especially here in Pittsburgh, can give you about 200 millirems per year. One thing to note is that these are very small amounts of radiation, with the exception of radon gas, which can cause a lot of damage over a longer period of time. For example, a few decades. This became a problem, especially for women who worked as housewives in the 1950s, who spent a lot of time in the basement doing laundry, especially here in Pittsburgh, who were exposed to a lot of these little amounts of radiation per year, which ended up causing a larger number of cancer cases. Therefore, it's very important when you move into a new home to measure the amount of radon in the basement, because although you're exposed to a small amount over a year, a buildup over several decades can be deadly. Now let's take a look at another application of radioactive decay, and that is to do certain types of dating. First of all, as a reminder, radioactive decay undergoes first-order kinetics, and we can use our integrated rate laws and half-life equations to do calculations that involve radioactive dating. Note that since the number of nuclei is directly related to the activity, we can use the ratio of activities or number of nuclei or amount of radioactive sample as a means to measure the age of a certain artifact. We can also, as we did in one of the previous examples, use the half-life equation to get the rate constant for our radioactive decay process. Let's do an application, which is carbon-14 dating. Living organisms, such as humans, plants, and many other living organisms, I guess, sorry, this is a little awkward, uptakes carbon dioxide from the atmosphere. When we're When a living organism is alive, the ratio between carbon-14 and carbon-12 remains the same since the organism is always taking in carbon dioxide from the atmosphere. Once the organism dies, however, it no longer uptakes carbon dioxide, and the carbon-14 begins to decay and decrease due to the beta decay of carbon-14. Therefore, if we know the activity of a living species versus a species which is no longer living, we can use the ratio between these activities to measure the date of the no longer living organism. This allows us to not only date fossils, which are remnants of living organisms, we can also date anything that is made from a living organism. For example, the picture on the right is a sample from the Dead Sea Scrolls, which was dated using carbon-14 dating. Another thing to note is that this also assumes that the amount of carbon dioxide in the atmosphere today is the same as it was in the time where the artifact was created. This is true for only a certain amount of time, a few hundred thousands of years. To date older objects, we need to use other isotopes that could exist, since the carbon dioxide level in the atmosphere has changed during different epochs in the history of Earth. Let's do an example calculation involving carbon-14 dating. A skull that is believed to belong to an early human has an activity of 4.50 disintegrations per minute per gram of carbon, which is just a unit of activity. If a living organism has a decay rate of 15.3 disintegrations per minute per gram of carbon, how old is the skull? We also know that the half-life of carbon-14 is 5,730 years. To tackle this problem, the first thing that we want to do is calculate the rate constant, because we'll need that to use in our integrated rate law. The rate constant is equal to the natural log of 2 over the half-life of the equation, or the half-life of the sample. This is equal to the natural log of 2 over 5,730 years, which is equal to 1.21 times 10 to the minus 4 inverse years. Note that, unlike the previous example, we're going to actually leave this rate equation, this rate constant, in terms of inverse years. This is because, as we're dating the sample will probably have an age of a few thousand years. Now let's look at our integrated rate law that says the natural log of the ratio between the original activity, and the activity at time t is equal to minus kt. We can substitute in our activities into the natural log ratio and also substitute in our rate constant. The natural log of the activities is equal, the rate of the ratio between the activities is equal to minus 1.22378. Therefore, the time, or the age of the human skull, is equal to 1.22378 divided by minus the rate constant. This gives us 1.01 times 10 to the 4th years, or about 10,000 years. Okay, thank you for listening to the lecture, and I apologize for any awkwardness. It's kind of awkward to give a lecture to my apartment. I kind of miss giving a lecture to you guys. So take care, guys, and stay safe and healthy.